Why the universe is so strangely stable. The universe didn't have to work. That's the strange part. It didn't have to hold together. It didn't have to make stars. It didn't have to produce anything interesting at all. And yet, here we are. You lying somewhere comfortable right now, made of atoms that were forged in the hearts of stars that died before our sun was born. You, breathing oxygen that was cooked inside a star, so massive it eventually exploded and scattered its insides across space. You, thinking thoughts with a brain built from carbon and nitrogen and trace amounts of iron, all of it assembled over billions of years by processes that follow the same simple rules everywhere in the cosmos. The universe works, and not just barely. It works in a way that allows for chemistry, for complexity, for planets and oceans, and eventually, somehow, for minds that can look up at the night sky and wonder why any of this exists at all. That's what we're going to think about tonight, not in a rushed way, not in a way that demands anything from you. You don't need to remember any of this. You don't need to take notes. You can let your eyes close whenever they want to. You can drift in and out. The ideas will still be here, moving gently in the background, like a river you can float on without needing to steer. We're going to talk about why the universe is the way it is, why the rules are the rules, why things hold together instead of flying apart, why stars shine, why atoms exist, why out of all the ways a universe could have been, this one seems so remarkably suited to producing structure and complexity and eventually life. There's no test at the end. There's no place you need to arrive. You're already where you need to be. So settle in, let your shoulders drop, let your breathing find its own rhythm, and let's begin. The first thing to know, and maybe the most comforting thing, is that the universe follows rules. Not rules that someone wrote down, not rules that change depending on where you are or when you're looking, just patterns, consistencies, the way things behave over and over again, reliably, predictably, everywhere we've ever looked. A stone falls the same way in your backyard as it would on the surface of the moon. Light travels at the same speed, whether it's coming from a lamp in your room or from a star a billion light years away. Atoms behave the same way in your body as they do in the atmosphere of a distant planet orbiting a star you'll never see. This is remarkable. It didn't have to be this way. Imagine a universe where the rules were different in different places, where gravity worked one way here and another way over there, where atoms held together in some regions but fell apart in others. That kind of universe would be chaotic, unpredictable. It would be very hard for anything interesting to happen in a universe like that. Structure wouldn't last, patterns wouldn't form. There would be no planets, no stars, no chemistry, no life. But our universe isn't like that. The rules are the same everywhere. The same gravity that keeps your feet on the ground also keeps the moon in orbit around the Earth, and the Earth in orbit around the Sun, and the Sun in orbit around the center of the Milky Way galaxy. The same electromagnetic force that lets you see these words also governs the behavior of plasma in the cores of stars millions of light years away. This consistency is the foundation of everything. It's why we can do science at all. If the rules kept changing, we'd never be able to figure anything out. But because the rules are stable, we can observe, we can measure, we can predict. And that's what humans have been doing for a very long time, looking at the sky, watching how things move, noticing patterns, writing them down, testing them, refining them. Over centuries, we've discovered that a surprisingly small number of rules govern an enormous amount of what happens in the universe. Gravity, electromagnetism, the strong force that holds atomic nuclei together, the weak force that governs certain kinds of radioactive decay. These four forces, combined with a handful of fundamental constants, seem to account for almost everything we observe. It's a bit like discovering that a symphony, with all its complexity, all its instruments, all its movements, can be written down using just a few musical notes. The notes are simple. The combinations are endless. Let's talk about those constants for a moment. They're worth understanding, even if just gently. A constant in physics is a number that doesn't change. It's a fixed value that appears in the equations describing how the universe works. The gravitational constant tells us how strongly mass attracts other mass. The speed of light tells us the fastest anything can travel. The charge of an electron tells us how strongly electrons interact with electromagnetic fields. There are about 24 of these constants that physicists have measured with great precision. Here's the interesting part. We can measure these numbers, but we can't explain them. We know what they are, but we don't know why they are. Why is the gravitational constant the value it is, and not some other value? Why does light travel at exactly 299,792,458 meters per second, and not faster or slower? Why does an electron have the charge it has? These questions don't have answers yet. Maybe they never will. Or maybe someday someone will discover a deeper theory that explains where these numbers come from. For now, all we can do is observe that these are the values and that the universe seems to depend on them in profound ways. Because here's the thing, if these constants were different, even slightly different, the universe would be a very different place. This is sometimes called fine-tuning. It's a way of describing how sensitive the universe is to the values of its fundamental constants. Consider gravity. Gravity is actually a very weak force compared to the other forces in nature. You can prove this to yourself right now. Pick up a small object, a pen or a phone. You've just overcome the gravitational pull of the entire Earth with the muscles in your hand. That's how weak gravity is. But imagine if gravity was stronger, not a lot stronger, just a little bit. In that case, stars would burn through their fuel much faster. They'd be hotter, brighter, and shorter-lived. The universe might not have time to produce the heavy elements needed for planets and life before all the stars burned out. On the other hand, if gravity were weaker, it might not be able to pull gas clouds together tightly enough to ignite nuclear fusion. Stars might never form at all. The universe would be a diffuse cloud of hydrogen, slowly cooling, never lighting up. The same kind of sensitivity applies to the other forces and constants. The strong nuclear force holds the nuclei of atoms together. Protons, which are positively charged, naturally repel each other. They don't want to be close together. But the strong force is strong enough to overcome that repulsion and bind protons and neutrons into stable nuclei. If the strong force were about 2% weaker, it couldn't do this job as well. Hydrogen would be the only stable element. No carbon, no oxygen, no iron, just hydrogen everywhere forever. If the strong force were about 2% stronger, hydrogen would fuse too easily. The early universe would have converted all its hydrogen into heavier elements almost immediately, leaving no fuel for long-lived stars. The universe would be full of burnt-out remnants, with no ongoing sources of light or heat. 2%, that's all it would take to make the universe unrecognizable. There's another constant worth mentioning, because it's one of the most striking examples of fine-tuning. It's called the cosmological constant, and it has to do with the expansion of the universe. The universe is expanding. Galaxies are moving away from each other. This has been happening since the Big Bang, about 13.8 billion years ago. But here's something that wasn't discovered until the late 1990s. The expansion is accelerating. Galaxies aren't just drifting apart, they're drifting apart faster and faster. The cosmological constant is a number that describes the strength of this acceleration. It's related to something called dark energy, which is a kind of energy that seems to permeate all of space and push things apart. The value of the cosmological constant is extraordinarily small. In certain units, it's about 1 part in 10 to the power of 120. That's a 1 followed by 120 zeros. It's an almost incomprehensibly tiny number. And yet, if the cosmological constant were even slightly larger, the universe would have expanded so fast in its early history that matter could never have clumped together. No galaxies, no stars, no planets. If it was slightly smaller or negative, the universe might have collapsed back on itself before anything interesting could happen. The fact that the cosmological constant sits in this narrow, life-permitting range is one of the most puzzling observations in all of physics. No one knows why it has the value it does. Some physicists think it's just a coincidence. Others think it points to something deeper, maybe a multiverse, where many different universes exist with different constants, and we happen to live in one where the constants allow for observers. But that's speculation. What we know for certain is that the constants are what they are, and that the universe, as a result, is capable of producing stars and planets and chemistry, and eventually us. Let's shift now to something a little more tangible. Let's talk about where the elements come from. You probably know that everything around you is made of atoms: the air you're breathing, the surface you're lying on, your own body. All of it is composed of tiny particles, atoms, that combine in different ways to form different substances. But where did those atoms come from? The answer is one of the most beautiful discoveries in the history of science. It connects the largest scales of the universe, stars and galaxies, to the smallest scales, individual atoms and nuclei, and it shows how deeply connected we are to the cosmos. In the very early universe, just moments after the Big Bang, there were no atoms at all. It was too hot. Energy was so intense that particles couldn't hold together. There was a kind of soup of fundamental particles, all colliding and scattering at incredible speeds. As the universe expanded, it cooled. And as it cooled, things began to settle down. Protons and neutrons formed. Then, in a brief window lasting only about 20 minutes, some of those protons and neutrons fused together to form the nuclei of the lightest elements: hydrogen, helium, and tiny amounts of lithium. That was it. That was all the Big Bang produced. Hydrogen and helium mostly, the two simplest elements. For a long time after that, the universe was dark. There were no stars yet, just vast clouds of hydrogen and helium gas, slowly cooling, slowly spreading out. But gravity was working. Gravity is patient. It doesn't care about time. It just pulls. And over millions of years, it began to pull those gas clouds together into clumps. The clumps got denser and hotter, and eventually, in the cores of those clumps, something remarkable happened. Nuclear fusion ignited. Nuclear fusion is the process that powers stars. It's what makes the sun shine. It's what makes every star in the night sky glow. Here's how it works in the simplest terms. When you squeeze hydrogen atoms together tightly enough and heat them to extremely high temperatures, millions of degrees, the nuclei of those atoms can fuse together to form a new element, helium. This process releases energy, a lot of energy. The reason is subtle and has to do with the fact that a helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. That missing mass gets converted into energy according to Einstein's famous equation, E equals mc squared. This energy is what makes stars shine. It's the light you see when you look up at the night sky. Every point of light is a furnace, fusing hydrogen into helium, releasing energy that travels across space and eventually reaches your eyes. But here's the thing, hydrogen can only take you so far. After a star has been fusing hydrogen for millions or billions of years, its core fills up with helium. The hydrogen runs low. And then what? If the star is massive enough, a new stage begins. As the hydrogen in a star's core gets used up, the core contracts. It gets denser and hotter, and if it gets hot enough, around 100 million degrees, a new kind of fusion can start. Helium nuclei begin to fuse together to form carbon. This is called the triple alpha process because it involves 3 helium nuclei, which are also called alpha particles, combining to form a single carbon nucleus. It's a delicate process. Helium nuclei don't naturally stick together. When 2 of them collide, they form a very unstable intermediate nucleus called beryllium-8, which falls apart almost instantly. But if, during that brief moment of existence, a 3rd helium nucleus happens to collide with the beryllium, carbon-12 is formed. And carbon-12 is stable. It sticks around. This is how carbon is made. Every atom of carbon in your body was made this way, inside a star, through this improbable sequence of collisions. And once a star has carbon, it can go further. If the core gets hot enough, carbon can fuse with more helium to form oxygen. Oxygen can fuse to form heavier elements, and the process continues, step by step, building up the periodic table. In the cores of the most massive stars, this process continues all the way up to iron. Iron is special. It's the most stable nucleus. Fusing iron doesn't release energy, it requires energy. So when a star's core fills up with iron, fusion stops. The star has reached the end of the line. And then something dramatic happens. Without fusion to push outward, the core of the star collapses under its own gravity. In less than a second, the core implodes. The outer layers of the star, which were being held up by the pressure from the core, suddenly have nothing supporting them. They fall inward, hit the dense core, and bounce back in a catastrophic explosion. This is a supernova. A supernova is one of the most energetic events in the universe. For a brief time, a single exploding star can outshine an entire galaxy. The explosion scatters the star's outer layers, all the elements it spent millions of years creating, into space. And here's the key part. In the intense conditions of a supernova, there's enough energy to fuse elements heavier than iron. Gold, silver, platinum, uranium, all of these heavy elements are forged in the fires of dying stars. The explosion sends these elements flying outward at tremendous speeds. They mix with the gas and dust floating between the stars. And over time, gravity pulls that enriched material together again, forming new stars, new planets, new moons. Our solar system formed from a cloud of gas and dust that contained the remnants of earlier stars. The sun formed at the center. The planets formed from the leftover material. And the Earth, with its iron core, its oxygen-rich atmosphere, its carbon-based life, is made of atoms that were cooked inside stars that died billions of years ago. This is not a metaphor. It's literally true. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was made inside a star. You are, in a very real sense, made of star stuff. Let's pause here for a moment. Let your breathing settle. Let your body relax a little more. You don't need to hold onto all of this. You don't need to remember the details. The ideas are just here, floating gently, like clouds drifting across a sky. The universe follows rules. Those rules are the same everywhere. A small number of constants determine how everything works. If those constants were even slightly different, the universe would be unrecognizable. Stars forge the elements. When stars die, they scatter those elements into space. New stars and planets form from that material. And eventually, on at least one planet, life appeared. Life that could wonder about all of this. That's the story so far. It's a story of consistency and patience, of simple rules leading to complex outcomes, of atoms assembling into stars, and stars assembling atoms, and atoms eventually assembling into beings that can look back and trace the whole process. There's more to explore, but there's no rush. We have time. One of the most interesting questions in all of science is this: how does complexity arise from simplicity? The laws of physics are at their core remarkably simple. A handful of forces, a handful of constants, equations that can fit on a single page. And yet, from these simple ingredients, the universe produces galaxies and stars and planets and oceans and forests and mines. How does that happen? The answer seems to involve something called emergence. Emergence is the idea that when many simple things interact, new properties can appear that weren't present in any of the individual parts. Think about water. A single molecule of water, two hydrogen atoms bonded to one oxygen atom, doesn't have the properties of wetness or fluidity. It doesn't have the properties of ice. It doesn't have the properties of steam. Those properties only emerge when you have billions upon billions of water molecules interacting together. Wetness is an emergent property. It exists at the level of the group, not the individual. The same principle applies throughout nature. A single neuron in your brain doesn't have thoughts, but billions of neurons connected in intricate networks produce consciousness. A single ant has no concept of colony management, but millions of ants, each following simple chemical signals, build elaborate underground cities with chambers and tunnels and ventilation systems. The whole becomes more than the sum of its parts. This is one of the deepest ideas in science, and it's still not fully understood. We can observe emergence happening, we can describe it, we can sometimes simulate it in computers, but we don't have a complete theory of how it works. What we do know is that emergence seems to require certain conditions. You need many parts, you need those parts to interact, you need feedback loops, where the behavior of the whole influences the behavior of the parts, and vice versa. And you often need a flow of energy through the system, keeping it out of equilibrium. The universe, it turns out, provides all of these conditions. And so, over billions of years, complexity has emerged at every scale. Atoms forming molecules, molecules forming cells, cells forming organisms, organisms forming ecosystems, minds forming societies. It's all emergence, all the way up. There's a tension at the heart of physics that's worth mentioning here. It has to do with order and disorder and with the direction of time. The second law of thermodynamics says that in an isolated system, entropy tends to increase. Entropy is a measure of disorder, or more precisely, a measure of how many different microscopic arrangements are consistent with a given macroscopic state. That's a mouthful, let's make it simpler. Imagine you have a box of gas. All the gas molecules are bouncing around randomly. Now imagine that, for a brief moment, all the molecules happen to end up in one corner of the box. That would be a very ordered, low-entropy state. There's only one way for all the molecules to be in the corner, but there are countless ways for them to be spread throughout the box. So statistically, the molecules will almost always be spread out. They'll move from the ordered state to the disordered state, not because anyone is directing them, but simply because disordered states are overwhelmingly more likely. This is the second law. Entropy increases because high-entropy states vastly outnumber low-entropy states. The second law has a profound implication. It gives time a direction. The future is the direction in which entropy increases. Eggs break but don't unbreak. Ice melts but doesn't spontaneously freeze in a warm room. Coffee cools, heat disperses, order decays. This is sometimes called the arrow of time. It's why we remember the past, but not the future. It's why causes precede effects. It's why the universe seems to be running down. And yet, and this is the tension, the universe is clearly capable of producing order. Stars form, planets form, life forms, minds form. How can this be if entropy is always increasing? The answer is subtle but important. The second law applies to isolated systems, but the Earth is not an isolated system. The sun pours energy onto the Earth constantly. That energy drives everything: the weather, the oceans, the plants, the food chain, your own metabolism. Life maintains its order by exporting disorder. You eat food, which is highly ordered. You digest it, extract energy, build and repair your body, and in the process, you release heat and waste, both of which are more disordered than the food you started with. So while your body maintains low entropy, the total entropy of you plus your environment increases. Life doesn't violate the second law, it rides it. It uses the flow of energy from the sun to create temporary pockets of order, all while contributing to the overall increase of disorder in the universe. This is true at every scale. Stars are temporary pockets of order in a universe trending toward disorder. Galaxies are temporary pockets of order. You are a temporary pocket of order. None of it lasts forever. The stars will burn out. The galaxies will fade. Eventually, the universe will reach a state of maximum entropy, a state sometimes called heat death, where nothing interesting can happen anymore. No gradients, no flows, no change. But that's trillions upon trillions of years away. In the meantime, the universe is slowly winding down, and as it winds down, it produces all this astonishing complexity along the way. There's something strangely comforting about this picture. The universe is not chaotic, it's not random, it follows rules. Those rules are consistent, they allow for complexity, they allow for emergence, they allow for patience, the slow unfolding of structure over cosmic timescales. And you are part of that unfolding. Your atoms came from stars. Your patterns of organization arose through billions of years of evolution. Your thoughts are electrochemical signals in a brain that emerged from the long interplay of physics and chemistry and biology. You don't have to do anything with this information. You don't have to remember it or act on it. It's just here, a quiet backdrop to your experience. The universe is the way it is. The constants are what they are. The rules apply everywhere. And somehow, against all odds, here you are, breathing, thinking, resting. Let your eyes stay closed if they want to. Let your thoughts drift if they want to. There's nowhere you need to go. Let's talk about scale for a while. It's one of the hardest things for human minds to grasp, but it's worth trying, even if just gently. The observable universe, the part of the universe we can see, is about 93 billion light-years across. A light-year is the distance light travels in 1 year. Since light moves at about 300,000 kilometers per second, a light-year is roughly 9.5 trillion kilometers, and the observable universe spans 93 billion of those. These numbers are meaningless to our intuitions. Our brains evolved to navigate savannas and forests, not cosmic voids. We are good at estimating distances like across the river or to the top of that hill. We're not equipped to feel the difference between 1 million and 1 billion, let alone between 1 billion and 1 trillion. But let's try anyway. Imagine you could fly from Earth to the moon. The moon is about 384,000 kilometers away. If you were traveling in a fast airplane, going 1,000 kilometers per hour, it would take you about 16 days to reach the moon. Now imagine flying to the sun. The sun is about 150 million kilometers away. At the same speed, it would take you about 17 years. Now imagine flying to the nearest star other than the sun. That's Proxima Centauri, about 4.24 light-years away. At 1,000 kilometers per hour, it would take you about 4.5 million years to get there. And Proxima Centauri is the nearest star. There are roughly 100 billion stars in our galaxy, and there are roughly 200 billion to 2 trillion galaxies in the observable universe. The numbers are so large they lose meaning, but maybe that's okay. Maybe the point isn't to comprehend the numbers, but to sit with the feeling of vastness, to recognize that we are small, that our lives are brief, that the universe extends far beyond anything we will ever see or touch. And yet, the same rules that govern the motion of planets around our sun also govern the motion of planets around distant stars. The same chemistry that makes water wet here makes water wet everywhere. The same elements that build our bodies are scattered throughout the cosmos. We are small, but we are not separate. We are made of the same stuff as everything else. We are part of the same story. Let your breathing slow now, if it hasn't already. Let your body sink a little deeper into whatever surface is supporting you. There's nothing you need to do, nothing you need to figure out. The universe is vast, the rules are simple. Complexity arises from simplicity, order emerges from the flow of energy, time moves forward, stars are born and die, elements are forged and scattered, planets form, life appears, minds awaken. And here you are, in this moment, resting quietly within all of it. One of the questions that lingers behind everything we've discussed is this: why these rules? We've talked about what the rules are. We've talked about what the constants are. We've talked about how sensitive the universe is to those values. But we haven't answered the deeper question: why are the rules the rules? Why do the constants have the values they have? The honest answer is that we don't know. Science is very good at describing how things work. It's less good at explaining why things are the way they are in the first place. We can measure the gravitational constant with extraordinary precision. We can use it to predict the motion of planets and satellites with incredible accuracy. But we cannot explain, from first principles, why gravity has the strength it does. The same is true for all the other constants: the speed of light, the charge of the electron, the strength of the nuclear forces. We measure them, we use them, we build technologies based on them, but their origins remain mysterious. Some physicists hope that there's a deeper theory waiting to be discovered, a theory that would explain all the constants as consequences of some more fundamental principle. String theory, for example, is one attempt at such a theory. It suggests that all the particles and forces we observe are manifestations of tiny vibrating strings of energy, and that the constants emerge from the ways those strings can vibrate. But string theory is unfinished. It hasn't made many testable predictions, and even if it did, it might just push the question back a level. Why these strings? Why these vibrations? Other physicists take a different approach. They suggest that our universe might be one of many, part of a vast multiverse in which different regions have different constants. In that picture, the question why these constants has a simple answer, because if the constants were different, we wouldn't be here to ask the question. We happen to live in a region where the constants permit observers, and that's why we observe these particular values. This is called the anthropic principle. It's controversial. Some see it as a genuine explanation. Others see it as giving up on the search for deeper understanding. The truth is, we don't know which view is correct. We may never know. The question of why the universe is the way it is may turn out to be one of those questions that science can't answer, not because science has failed, but because the question lies beyond the reach of experiment and observation. And maybe that's okay. Maybe it's okay to live with mystery. Maybe it's okay to acknowledge that some questions don't have answers, or that the answers are forever beyond our grasp. There's a kind of peace in that, if you let yourself feel it. The universe doesn't owe us explanations. It doesn't owe us meaning. It simply is. And somehow, within that vast, indifferent cosmos, pockets of complexity have arisen that can ask questions, seek understanding, feel wonder. That's remarkable. That's worth appreciating, even if we never understand it fully. You don't have to solve the mysteries of existence tonight. You don't have to figure anything out. You're allowed to simply rest within the mystery, to let it hold you without demanding answers. The universe is very old. About 13.8 billion years have passed since the Big Bang. That's a number, like the others, that's hard to feel, but let's try to get a sense of it. Imagine the entire history of the universe compressed into a single year. The Big Bang happens at midnight on January 1st. The first stars begin to form sometime in January. Our galaxy, the Milky Way, takes shape around March, but the Sun and Earth don't form until September, around September 2nd. For months after that, life on Earth is just single-celled organisms. Fish appear around December 17th. Dinosaurs appear on Christmas Day. They go extinct on December 30th. Humans, we show up on December 31st, in the final minutes of the final day. All of recorded human history, every empire, every war, every book, every song, takes place in the last few seconds before midnight. That's how brief we are. That's how recent. The universe spent billions of years preparing the stage before we arrived. And yet, in that brief flash, we've managed to learn so much. We've figured out how stars work. We've traced the origins of the elements. We've sent spacecraft to other planets. We've detected ripples in spacetime from colliding black holes. We've peered back in time to the cosmic microwave background, the faint glow left over from the early universe. We're a young species, on a small planet, orbiting an ordinary star in one of billions of galaxies. And somehow, we've begun to understand the universe we live in. That's not nothing. That's something worth appreciating, even as you drift towards sleep. Let's slow down now, let the pace ease, there's no hurry. The night sky, if you can see it, is full of light. Each point of light is a star, or sometimes a galaxy. Each star is a furnace, fusing atoms, shining across space. The light you see left those stars years or decades or centuries ago. Some of it has been traveling longer than human civilization has existed. When you look at the night sky, you're looking back in time. You're seeing the universe as it was, not as it is. The light from distant galaxies shows us what those galaxies looked like billions of years ago. In a sense, the night sky is a time machine. It lets us see the past simply by looking up. And all of that light, all of that energy, all of those distant suns, they're governed by the same rules that govern the candle on your table, the bulb in your lamp, the glow of your phone screen, the same electromagnetism, the same quantum mechanics. the same relationships between energy and matter. The universe is consistent. It doesn't play favorites. It doesn't make exceptions. The rules are the rules everywhere, always. There's something restful in that, something you can trust. The universe may be vast and mysterious, but it's not capricious. It follows patterns, it behaves reliably, and that reliability is what makes understanding possible. Your body is relaxing now, or perhaps it has been relaxing all along without you noticing. That's fine, let it happen. The atoms in your body are the same kinds of atoms that exist in the farthest reaches of space. Hydrogen, carbon, oxygen, nitrogen, calcium, iron, the same building blocks assembled into different forms. Those atoms have been on long journeys. The hydrogen in your body is among the oldest stuff in the universe, forged in the first few minutes after the Big Bang. The heavier elements came later, cooked inside stars, scattered by supernovae, gathered into clouds, pulled together by gravity, incorporated into planets, cycled through oceans and rocks and living things for billions of years. And now, for a little while, those atoms are arranged into the pattern that is you. They hold their shape. They do their jobs. They'll eventually disperse again, return to the cycle, become part of something else. But right now, they're you, and you're here, and you're resting. The universe doesn't ask anything of you. It doesn't require your participation. It was here before you, and it will continue after you. The stars will keep shining. The galaxies will keep drifting. The rules will keep applying. You're not separate from any of this. You're part of it. A temporary arrangement of matter and energy, aware of itself for a brief moment in cosmic time. A pocket of complexity in an ocean of entropy. A mind that can wonder. There's no task you need to complete. No destination you need to reach. You're already where you're supposed to be. The night is quiet, or maybe it's not. Maybe there are sounds around you, traffic or wind or the hum of a machine. That's okay too. Let the sounds be part of the background. Let them blend into the stillness. Your thoughts may be drifting now. That's fine. Let them drift. They don't need to be organized. They don't need to make sense. They can float like leaves on a stream, moving wherever the current takes them. The universe is the way it is. The rules are the rules. The constants are set just so, and from that simple foundation, everything arises. Stars and planets and moons, oceans and mountains and forests, cells and organs and bodies, minds and memories and dreams. All of it connected, all of it part of the same story. Let your breathing continue at its own pace. Let your body continue to settle. There's nothing you need to do. The story of the universe is still unfolding. New stars are being born right now, in clouds of gas and dust scattered throughout the galaxy. Planets are forming around those stars. The elements are cycling, being built and scattered and gathered again. Somewhere in some distant corner of the cosmos, something interesting may be happening. Something we'll never know about. Something that follows the same rules, uses the same elements, emerges from the same processes. Or maybe not. Maybe we're alone. Maybe this planet is the only place where life has taken hold. We don't know. We may never know. But either way, the universe continues. The rules apply. The constants hold steady, and the slow unfolding goes on. You don't need to stay awake for any of this. You can let yourself drift. The ideas will still be here. The universe will still be here. Nothing depends on your attention. Sleep, if it comes, is its own kind of rest. Your body will repair itself. Your mind will consolidate memories, process experiences, dream. The processes are automatic. You don't need to supervise them. And while you sleep, the earth will continue turning. The stars will continue shining. The galaxies will continue their slow dance through the void. You're held by the same gravity that holds the planets in their orbits. You're made of the same atoms that make the stars. You're governed by the same rules that govern everything. There's a kind of belonging in that, a quiet kinship with the cosmos. You're not a stranger here, you're a native, you're made of this place. Let the thoughts fade now if they want to. Let the words become softer. Let the meaning dissolve into feeling. The universe is the way it is. You are the way you are. And for now, that's enough. Continuing in Part 2. Part 2. The night continues. Time passes as it always does, in its quiet, steady way. The earth rotates. The stars wheel slowly overhead, though you may not be able to see them from where you are. It doesn't matter. They're there whether you see them or not. And you're still here, resting, breathing, perhaps drifting somewhere between wakefulness and sleep. That's a good place to be. There's no pressure to be fully one or the other. You can float in that in-between space for as long as you like. We've been thinking about why the universe is the way it is. We've talked about the rules, the constants, the fine-tuning. We've talked about where the elements come from. We've talked about emergence, how complexity arises from simplicity. We've talked about entropy and the arrow of time. Now let's talk about something gentler. Let's talk about patterns. The universe is full of patterns, not just the mathematical patterns that physicists study, but visible, tangible patterns that you can see and feel. Think about spirals. Spirals appear everywhere, in the shape of galaxies, in the arrangement of seeds in a sunflower, in the curl of a seashell, in the swirl of water going down a drain, in the structure of a hurricane viewed from space. Why spirals? There's no single answer, but part of it has to do with how things rotate and grow. When something is both turning and expanding, spirals naturally emerge. It's a consequence of the geometry of space and the dynamics of motion. Or think about branching. Trees branch, rivers branch, lightning branches, blood vessels branch, lungs branch, neurons branch. The same basic pattern, a main trunk dividing into smaller and smaller extensions, appears in systems that have nothing in common except the way they distribute resources or energy. These patterns aren't designed, they emerge. They arise from simple rules applied over and over again. They're examples of the universe finding efficient solutions to common problems. There's something reassuring about patterns. They suggest that the universe is not random. Even when things seem chaotic, there's often an underlying order. Even when things seem unpredictable, there are regularities waiting to be discovered. Scientists spend their careers looking for patterns. That's really what science is, the search for patterns in nature and the attempt to explain them. When a pattern is found and explained, we call it a law or a theory. But before it's explained, it's just a pattern, a hint, a clue that there's something to understand. The history of science is full of moments when someone noticed a pattern that others had missed. Isaac Newton noticed that the same force pulling an apple to the ground also kept the moon in orbit. James Clerk Maxwell noticed that electricity and magnetism were two aspects of the same phenomenon. Charles Darwin noticed that species seemed to be related to each other in ways that suggested common ancestry. These insights didn't come from nowhere. They came from paying attention to patterns, from asking, why does this keep happening? What connects these seemingly different things? You don't need to be a scientist to appreciate patterns. You see them all the time. The rhythm of day and night, the cycle of seasons, the phases of the moon, the regularity of tides. These patterns were noticed long before science existed. Ancient peoples tracked the movements of the stars and planets. They built calendars. They predicted eclipses. They didn't understand the physics behind what they saw, but they recognized the patterns and used them to organize their lives. In a sense, recognizing patterns is one of the most fundamental things minds do. It's how we learn, it's how we predict, it's how we make sense of a complicated world. And patterns are comforting. They let us know what to expect. They reduce uncertainty. They make the future feel a little less unknown. The universe, at its largest scales, has patterns too. Galaxies aren't scattered randomly through space. They're organized into groups and clusters and superclusters, connected by filaments of matter, separated by vast, empty voids. The whole structure looks a bit like a cosmic web, threads of galaxies stretching across billions of light years. This structure emerged from tiny fluctuations in the early universe. Right after the Big Bang, the universe was almost perfectly uniform, but not quite. There were tiny variations in density, regions that were slightly more or less dense than average. Over billions of years, gravity amplified these variations. Denser regions attracted more matter and became even denser. Less dense regions lost matter and became emptier. And the result is the cosmic web we see today. It's a pattern that spans the entire observable universe, and it arose from the simplest possible process, gravity pulling on matter over a very long time. Patterns in time are just as important as patterns in space. The universe has a history, it had a beginning, and it's been changing ever since. In the beginning, if that's even the right word, the universe was hot and dense. So hot that atoms couldn't form, so dense that everything was packed together in an unimaginably small volume. Then it expanded, it cooled, and as it cooled, new things became possible. First, atomic nuclei formed, then much later, atoms, then clouds of gas, then stars, then galaxies, then planets, then on at least one planet, life. This is not a random sequence. Each stage created the conditions for the next. Stars couldn't form until there was gas. Planets couldn't form until there were heavy elements. Life couldn't form until there was chemistry, each step built on the one before. The universe has a direction. It's going somewhere, not in the sense of having a destination, but in the sense of unfolding in a particular order. Simple things came first, complex things came later, and the story is still being written. You are part of that story, not a main character perhaps, not even a minor character, more like a single word in a very long book, but still part of it, still connected to everything that came before. Your existence depends on the Big Bang happening the way it did, on stars forming and dying the way they did, on the Earth forming in the habitable zone of a stable star, on billions of years of evolution, on countless accidents and coincidences and contingencies. Change any one of those things and you wouldn't be here. Someone else might be, or no one. The specific pattern that is you depends on everything that led up to this moment. That's not a burden, it's just a fact. And it's kind of amazing when you think about it, all of cosmic history leading up to this, to you lying here, breathing quietly, resting. Let your body relax a little more, let your mind settle a little more. There's no urgency, there's no deadline. The universe took billions of years to produce this moment. A few more minutes of rest won't matter. We've talked about a lot of things tonight, the rules of the universe, the constants, the elements, emergence, entropy, patterns, scale, history. But there's one more thing worth mentioning, and it's perhaps the most mysterious of all. Consciousness. You are aware, you are experiencing something right now. There is something it is like to be you, that's consciousness, and no one knows how it arises. We know that consciousness is related to brains. Damage the brain and consciousness changes. Alter the brain's chemistry and experience changes. There's clearly a connection between the physical stuff, neurons, synapses, electrochemical signals, and the subjective experience of being aware. But how does that connection work? How does activity in a network of neurons produce the felt quality of experience? Why does it feel like anything at all to be a brain processing information? These questions have puzzled philosophers and scientists for centuries. They're sometimes called the hard problem of consciousness. And despite enormous progress in neuroscience, we don't have a good answer. Some people think consciousness is just what brain activity looks like from the inside. Others think it's something more fundamental, woven into the fabric of reality itself. Others think it's an illusion, though it's hard to make sense of that idea, since the illusion itself is an experience. We don't need to resolve this mystery tonight. It's okay to leave it open. It's okay to admit that we don't know. What we do know is that you're conscious right now. You're aware of these words, or at least some of them. You're aware of your body, of your surroundings, of your thoughts drifting in and out. That awareness is precious, not because it's rare in the cosmic sense, we don't know how rare it is, but because it's the lens through which you experience everything. Without consciousness, the universe would exist, but there would be no one to appreciate it, no one to wonder about it, no one to feel awe or curiosity or peace. You are the universe experiencing itself. That's not a mystical claim. It's just what consciousness is, matter arranged in such a way that it becomes aware of itself and its surroundings. Stars don't know they're stars, rocks don't know they're rocks, but you know you're you, and you know you're part of something vast and ancient and still unfolding. Sleep is a strange state, a temporary suspension of consciousness, a daily rehearsal for the deeper mystery of death, and yet we need it, our bodies need it, our minds need it. During sleep, your brain is busy. It's consolidating memories. It's pruning unnecessary connections. It's restoring balance. It's dreaming, generating experiences that can seem just as real as waking life, even though they're conjured entirely from within. You don't have to understand sleep to benefit from it. You just have to let it happen. The processes are automatic. They've been refined over millions of years of evolution. So if sleep is coming for you now, let it come. Don't resist. Don't worry about missing something. The universe will still be here when you wake up. The night is long or short. It depends on how you measure it. In human terms, a night is a handful of hours. In cosmic terms, it's nothing, a blink, less than a blink. But in the terms that matter to you, the terms of your own experience, the night is as long as it feels. And right now, it probably feels soft, slow, gentle. That's the pace we've been moving toward all along, starting with curiosity, moving through information, and gradually slowing down, letting the pace ease, letting the words become softer and the ideas more diffuse. The universe is the way it is. We don't know why, we may never know why, but we know that it's consistent. We know that it follows rules. We know that it's capable of producing complexity. We know that it's produced us. And we know that right now, in this moment, you're part of it. A temporary arrangement of atoms, a brief flicker of consciousness, a pattern in the cosmic tapestry. You don't have to be anything more than that. You don't have to achieve anything tonight. You don't have to understand anything you don't already understand. You're allowed to simply be, to rest, to drift. The stars are still shining. They were shining before you were born, and they'll keep shining after you're gone. Some of them have already died. The light we see is ancient, left over from stars that exploded millions of years ago. We're seeing ghosts, echoes of light. But that doesn't make the light less real. It's still reaching us, still crossing the void, still arriving at our eyes and our telescopes and our cameras. The universe communicates through light, through gravity, through the slow, patient processes of physics and chemistry, and we've learned to listen. We've learned to read the messages. That's what all of science is, really, learning to read the universe's messages, decoding its patterns, understanding its language. Your breathing has probably slowed by now. Your body has probably softened. Your thoughts may be drifting, unfocused, no longer trying to track every word. That's fine, that's good, let it happen. The words will continue for a while longer. You can follow them or not. You can drift in and out. The story doesn't require your attention to keep going. Imagine for a moment that you could see the universe from outside, not from Earth, not from a spaceship, but from some impossible vantage point beyond space and time. What would you see? You'd see a vast web of galaxies stretching in every direction, each galaxy containing billions of stars, many of those stars orbited by planets. On some of those planets, perhaps life. On some of those, perhaps minds. You'd see time flowing, the universe expanding, cooling, evolving, stars being born and dying, elements being forged and scattered, structures rising and falling. And somewhere in that immensity, you'd see a small blue planet orbiting an ordinary yellow star in the outer arm of an ordinary spiral galaxy. A planet covered mostly in water, with a thin atmosphere teeming with life. And on that planet, in this moment, you'd see billions of people going about their lives, working, sleeping, loving, suffering, wondering. And one of them is you, lying somewhere comfortable, breathing quietly, resting. You're so small from that vantage point, so brief, a spark that flickers for a moment and then fades. But that spark is real, that spark is aware, that spark is part of the universe knowing itself. And that's not nothing, that's everything you have. That's the only window you'll ever have onto existence. The universe doesn't care about you in the sense that a person might care. It doesn't have preferences or intentions. It's not rooting for you or against you. But it produced you. It made you possible. The same laws that govern the motion of galaxies also govern the beating of your heart. The same forces that bind atomic nuclei also bind the molecules in your cells. You belong here. You're made of this place. You're not an accident or an intruder. You're a natural consequence of the way things are. Let that sink in if it wants to, or let it float away if it doesn't want to stay. There's no test. There's no requirement. Just rest, just breathe, just be. The night continues. The earth turns. The stars wheel slowly overhead. And you're here, part of it all, for this little while. There's a kind of peace that comes from understanding, or at least glimpsing, how things fit together, how the rules work, how the elements were made, how complexity arises, how you came to be here. It's not a peace that answers every question. It's not a peace that eliminates mystery. It's more like the peace of recognizing that you're part of something vast and ancient and still unfolding. You don't have to control it. You don't have to understand it fully. You just have to be part of it. And you always have been. Since the first atoms formed, since the first stars ignited, since the first cells divided, since the first minds awakened, you've been implicit in the story. Not you specifically, not the particular arrangement of atoms that you are now, but the possibility of you, the thread that would eventually become you. That thread stretches back 13.8 billion years. It connects you to the Big Bang, to the first stars, to the supernovae that forged your elements, to the cloud of gas that collapsed to form the sun, to the swirl of debris that became the earth, to the chemistry that became life, to the evolution that became minds. You're the current endpoint of a very long story, not the final endpoint, just where the story has gotten to so far. Tomorrow the story will continue, the universe will keep unfolding, new stars will form, old stars will die, planets will be born, life will persist or perish, minds will wander. And you'll wake up, probably, and go about your day. You'll eat and work and talk and think. You'll be a small part of the ongoing process. But for now, the story pauses. For now, you rest. The night is quiet, or maybe it's not. Either way, you can let the sounds blend into the background. You can let the thoughts blend into the background. You can let everything blend into a soft, undifferentiated haze. Sleep is coming, or it's already here. It doesn't matter which. You're safe either way. You're held by the same gravity that holds the planets. You're made of the same atoms that make the stars. The universe is the way it is. You are the way you are. And for now, for this moment, everything is exactly as it should be. Rest now, let the words fade, let the meaning dissolve. You don't need to hold onto anything. You don't need to remember anything. You can simply drift. The stars are shining, the galaxies are turning, the universe is unfolding. And you're part of it, a small, brief, beautiful part. Rest. The night continues. The earth turns. The universe goes on. And you can let go. There's nothing more you need to do. Nothing more you need to know. Just breathe. Just rest. Just be. The universe is still here. The stars are still shining. And you're exactly where you need to be. Rest now. Rest.